Assalamualaikum and hi, my name is Muhammad Aizat from Group C. Today I as a presenter will share with you about topic 2D flow fluid plate for assignments CFD for fluid mechanics 2. Table of content. First I will talk about group member and their tasks. Second, introduction about the flow fluid plate, and third about theory, objective, simulation video, and discussion. About group member, we have 4 group member. First is Siti Asnida binti Muhammad Noor as a preparing slide for presentation. Kamal Idham bin Jamal as a analysis CFD video. Me, Aizat, as a leader and a presenter. And lastly, Zakwan bin Muhammad Zaki as analysis CFD video. Introduction about CFD. Computational Fluid Dynamics (CFD) is a simulation of fluid mechanics flow using computational fluid dynamics (CFD) are the key to solve many problems in mechanical engineering. It has been used to understand fluid flow behavior. It is essential in design and developing any environment application. One of the most common problems is flow behavior in the boundary layer. Our aim to consider flow over a flat plate produce boundary layer problem of incompressible flow. The solution of the 2D laminar boundary layer of an incompressible flow formed on a semi-infinite plate has been introduced by Berlioz using the similarity solution in 1908. Then in 1983, Howard gave a new solution using the Runge-Kutta method for analyzing the flow over the flat plate. Our work is motivated by the desire to apply the CFD simulation of flow over a flat plate. Next is theory. Two-dimension flow flat plate is an air flowing past a solid surface will stick to the surface. This phenomenon caused by a viscosity is a description of the non-slip condition. This condition states that the velocity of the fluid at the solid surface equals the velocity of the surface. The result of this condition is that a boundary layer is formed in which the relative velocity varies from 0 at the wall to the value of the relative velocity at the some distance from the flat plate. First, the boundary layer equations are derived. This derivation and the assumption require in derivation in some detail. Second, the boundary layer equations are solved analytical and numerical for the case of laminar or turbulent flow. Fluid motion is said to be two-dimensional when the velocity at every point is parallel to a fixed plane and is the same everywhere on a given normal to the plane. Figure 5.1 suppose that the fluid in the region R boundary layer by the curve because the fluid is compressible, which essentially means that its density is uniform and constant. Fluid continuity requires that the rate at which the fluid flow into the region R. From right to the left in figure 5.1 across the curve ABP is equal to the rate at which it flows out of the region from right to the left across the curve ACP. The rate of flux flow across the surface is generally termed the flux. Thus the flux per unit length parallel to the z-axis from the right to the left across ABP is equal to the flux from right to left across ACP. Because ACP is arbitrary, it's flow that the flux from right to the left across any curve joining a point A and P is equal to the flux from the right to the left across ABP. In fact, once the base point A has been chosen, this flux only depends on the position of point P and the time. In the other word, if we denote the flux by, then it's solve a function of the location of P and the time. Boundary layer of a flat plate. Consider a flat plate is a length, an infinite width and negligible thickness that lies in the xz plane and whose two edges correspondent to x equal to 0 and x equal to L. Suppose that the flat plate is immersed in a low viscosity fluid whose unperturbed velocity fields. As we can see in figure 8.4, in the invis limit, the appropriate boundary condition at the surface of the plate v y-axis equal to 0 corresponding to the requirement of z normal velocity is already satisfied by the unperturbed flow. Hence, the original flow is not modified by the presence of the plate. However, when we take the finite viscosity of the fluid into account, an additional boundary condition Vx equal to 0 corresponding to the no-slip condition must be satisfied at the plate. The imposition of this additional constraint cause thin boundary layer of thickness bigger than L to form above and below the plate. This fluid flow outside the boundary layer remains effectively inviscid, whereas that inside the layer is modified by viscosity. It flows that the flow external to the layer is unaffected by the presence of the plate. Hence, the tangential velocity at the outer edge of the boundary layer is equal. Fourth is objective. Our objective is the aim of the analysis is to observe the boundary layer formation with the velocity profile near the flat plate. Next, number 5 is a simulation video explain about geometry detail and dimension, inlet, outlet and boundary, and also meshing nodes. This simulation will be given in the next video.
Hello everyone, this is the ANSYS Fluent tutorial. First, you have to drag and drop fluid flow to the right and make sure that you change the analysis type when you click on geometry. Make sure to change the analysis type to 2D, then just double click on geometry until the space claim open up. When the space claim open up, we have to make a flat plate into an XY plane, so we have to change the coordinate of sketch plane to XY. Then we have to set the dimension of we click on the rectangle and then we have to set the dimension of the rectangle. You may click on the dimension and set the dimension. For example, we set the dimension for 500 millimeter and another one is 1 meter. And then after the dimension, we click on mesh and waiting for the 3D mode surface to create it. Then after the 3D mode surface was created, check all the mesh, check the condition of the mesh, then after that close the mesh. Then you see that it's already updated. So now double click on setup and we can set that the fan is start up. So here that you think are being loaded. First, double click on model and make sure that the energy is set to off, and the viscous is lamina. Then we go to material, double click on material and double click to the air. Then we go to boundary condition. Double click on the boundary condition and set the inlet, and double click the inlet. Then we go to outlet and double click the outlet. After that, you may go to method and just keep it as default. Then we move to the monitor, double click on monitor, then we go to residual and double click on the residual. Then we move to the initialization. Check the condition of the initialization and then we click the initialize. After that, when it seems like no problem, we move to the run calculation and we do the iteration for 1000 to see how far it goes or how far it progress. So just click on calculate and we will monitor the convergence on the right. So as you can see, the convergence is fast, and you see that after like 300 iteration, and the residual like the continuity xy velocity and other thing has dropped to 1. Then we close this one and we go to the result. In order to show some result, just double click and we can take a look at the boundary layer. Then we can make a contour plot of velocity, and the location will be symmetry 1 and the variable is velocity, and we set it like a 20 contour, and you can see the boundary layer shown in contour plot. It also can show the pressure by just changing the variable to pressure, and you see the pressure field in this domain. We also can make some vector plot and choose symmetry 1 and deselect contour plot and click apply, then see that close to the wall. The boundary layer is shown quite interestingly. Here is your boundary layer. You also can make a line, can insert a line in the boundary layer. And you have to set point 1 and point 2, then click apply. After that, we move to the insert again and click on chart and move to the data series. Then set the location of line 1, Then move to the x-axis and set the variable to velocity, and then move to the y-axis and set the variable to y-axis, then click apply. And then you can see the base type of the boundary layer.
Lastly is a discussion. Result and discussion. Hydrodynamic boundary layer. From the figure 1 and 2, introduce the velocity distribution for the flow over the plate. The velocity at the plate is the lowest and it increases till become uniform in the invis area, which located above the boundary layer edge. The maximum velocity, the maximum value of the velocity decreased from the left side to the right side, far from the inlet. The maximum value of the velocity was 1.087 milli per second. The velocity vector along with the plate, as we can see in the figure 2, show that the velocity of fluid particles at the plate is 0 due to the non-slip condition, and this occurs due to the viscosity effect where the fluid particles stuck to the plate. The highest pressure was located near the leading edge and become lower as we go close to the outlet, as we can see in the figure 3. That's all for our group. Thank you.